To understand chemistry, we have to start small, really small. We're talking about atoms, the universe's fundamental Lego bricks. Everything you see, touch, or smell is built from these tiny building blocks. At the center of every atom is the nucleus, a VIP lounge packed with protons and neutrons. Protons have a positive charge and define the element. 6 protons means carbon, 8 means oxygen. Neutrons are neutral and help keep the nucleus stable. Orbiting the nucleus are electrons, tiny, energetic, and negatively charged. In a neutral atom, protons and electrons are balanced, creating stability. Electrons occupy specific energy levels or shells around the nucleus. Atoms are mostly empty space. If the nucleus were a marble, the electron would be 2 miles away. The reason you don't fall through the floor. Electrons in your shoes repel those in the floorboards. Chemistry is the dance of these charged particles. Once you understand atoms, you're on your way to understanding everything, and that's where all of chemistry begins. Atoms are defined by their protons, the tiny positively charged particles at the heart of every atom. The number of protons in an atom's nucleus is what makes each element unique, like a fingerprint for matter itself. But with so many elements, how do we make sense of them all? How do scientists keep track of the building blocks of everything around us? Enter the periodic table, the ultimate scientific cheat sheet. A tool so powerful it's used by chemists, physicists, and students worldwide. It's more than just a classroom poster. It's a map to the universe of elements, a phone book listing their details, and even a personality profile revealing how each element behaves. The table is arranged in horizontal rows called periods and vertical columns called groups, each with its own special meaning. As you move across a period from left to right, you add 1 proton to the nucleus and 1 electron to the outer shell, gradually changing the element's properties. Elements in the same group share the same number of valence electrons, the outermost electrons that do all the bonding and reacting, making them behave like chemical siblings. Group 1 elements, known as the alkali metals, have a single valence electron and are eager to give it away, making them highly reactive, especially with water. Group 17 elements, the halogens, are just 1 electron short of a full outer shell and desperately want to gain one, making them some of the most reactive nonmetals. Group 18, the noble gases, already have full outer shells. They're famously unreactive, rarely forming compounds, and are content to stay out of the chemical drama. By looking at an element's position on the table, you can predict its chemical personality, how it will react, what it will bond with, and even its state at room temperature. The periodic table isn't just a list, it's a living story of how elements interact, combine, and transform, shaping everything from water to stars. It tells us who's reactive and explosive, who's stable and precious, and who's too cool to mingle with anyone else. Master the table, and you unlock the secrets of chemistry, gaining the power to predict and understand the behavior of matter itself. It's the ultimate guide to the elements' cosmic party, where every element has a role, a personality, and a story to tell in the grand dance of the universe. Atoms are usually balanced, but what if they gain or lose electrons? They become ions, charged versions of themselves. Lose electrons and you get a positive ion or cation. Gain electrons and you get a negative ion or anion. Sodium loses an electron to become Na+, while chlorine gains one to become ClR. This electron swapping is the basis for many chemical reactions, but there's more. Atoms of the same element can have different numbers of neutrons. These are isotopes. Carbon-12 has 6 protons and 6 neutrons. Carbon-14 has 6 protons and 8 neutrons. Isotopes behave the same chemically, but can have different physical properties. Some isotopes, like carbon-14, are radioactive and decay at predictable rates, useful for dating ancient materials. So ions change charge, isotopes change mass, but both add fascinating layers to the world of atoms. Chemistry is all about these subtle differences. Ions and isotopes make the atomic world dynamic and diverse. That's what keeps chemistry interesting. Atoms are the tiny building blocks of everything around us, and at their core, they're always seeking stability. This quest for balance drives them to interact with other atoms, often by forming bonds that help fill their outer electron shells. It's a bit like a puzzle, each atom looking for the perfect fit to complete itself. Chemical bonds are the invisible threads that hold atoms together, transforming them into molecules and compounds. These combinations make up every material we encounter, from the air we breathe to the water we drink and even the cells in our bodies. Take ionic bonds, for example. They form when one atom donates an electron to another, creating oppositely charged ions that are powerfully attracted to each other. This is how sodium and chlorine come together to make table salt, a substance essential to life. Covalent bonds, on the other hand, are all about sharing. Here, 2 non-metals share electrons, so both can fill their outer shells. Water, or H2O, is a classic example. Its unique properties come from the way hydrogen and oxygen share electrons. Depending on how many electron pairs are shared, atoms can form single, double, or even triple bonds. Each type of bond changes the strength and flexibility of the molecule, affecting how it behaves. Then there are metallic bonds. A sea of electrons flows freely among metal atoms, creating a flexible, conductive structure. This is why metals can conduct electricity, be hammered into sheets or drawn into wires without breaking. These different types of bonds explain why metals are shiny and bendable, while salt crystals are hard and brittle. The way atoms connect shapes the world's textures and strengths. The type of bond at the atomic level determines a substance's melting point, hardness, solubility, and so much more. It's the reason why water flows, salt shatters, and metals gleam. Whether atoms are sharing, trading, or pooling their electrons, bonding is chemistry's magic trick, turning simple elements into the complex materials that make up our universe. Every object you touch, every material you see is shaped by these invisible forces. From the plastic in your phone to the water in your glass, chemical bonds are at work everywhere. Understanding how atoms bond is the key to unlocking the secrets of matter. It's the foundation of chemistry, and it helps us design new materials, medicines, and technologies. Chemical bonds are like the glue that holds not just objects, but the entire universe together, from the smallest molecule to the largest galaxy. And it all begins with atoms striving for a little more stability, reaching out to connect and create something greater than themselves. That's the true magic of chemical bonds, turning the ordinary into the extraordinary, one connection at a time. Not all covalent bonds share electrons equally. This leads to polarity. Some atoms are more electronegative, pulling electrons closer and creating a molecule with positive and negative ends, like water. Polar molecules act like tiny magnets, while non-polar molecules share electrons evenly. This difference affects how molecules interact, polar with polar, non-polar with non-polar. Intermolecular forces like hydrogen bonds are strong attractions between molecules, giving water its high boiling point. Weaker forces like van der Waals arise from temporary shifts in electron clouds, affecting even non-polar molecules. These forces determine if a substance is a solid, liquid, or gas at room temperature. The way molecules attract or repel shapes everything from water droplets to wax candles. Chemistry is about how things get along, or don't, at the molecular level. Polarity and forces are the secret handshake of the molecular world. Matter comes in three main states: solid, liquid, and gas. The state depends on a tug-of-war between particle energy and intermolecular forces. In solids, particles are locked in place, vibrating but not moving freely. Think of people stuck in theater seats. Solids have definite shape and volume. Add energy and particles break free. Now you have a liquid. Particles slide past each other like a crowd mingling in a lobby. Liquids have definite volume but take the shape of their container. Add even more energy and particles escape completely. Now it's a gas, spreading out to fill any space. Gases have no definite shape or volume. The state of matter is a balance between energy and attraction. Change the energy and you change the state. That's the secret behind melting, boiling, and freezing. Most things in nature are mixtures, not pure substances. A solution is a uniform mixture, like salt dissolved in water, where the solute is evenly spread in the solvent. Like polar solvents dissolve polar substances, non-polar dissolves non-polar. If particles are too big to dissolve, you get a suspension, like muddy water, where particles eventually settle out. In between is a colloid, where particles are small enough to stay mixed, but large enough to scatter light. Think milk or fog. Mixtures can usually be separated by physical means, unlike compounds. Solutions, suspensions, and colloids make up the messy, fascinating world around us. Each type has unique properties and uses. Understanding mixtures helps us make everything from medicines to mayonnaise. Chemistry is all about mixing things up, literally. That's how we get the variety of materials in our world. Chemistry is about transformation. Chemical reactions turn reactants into products. Atoms aren't created or destroyed, just rearranged, thanks to the law of conservation of mass. Chemical equations show this process, with reactants on the left and products on the right. Balancing equations ensures the same number of each atom on both sides. The mole is chemistry's counting unit. 6.022 x 10 circumflex 23 particles, making it possible to measure atoms by weighing them. Stoichiometry is the recipe book for reactions, telling us how much of each substance is needed. Reactions come in types: synthesis, building up; decomposition, breaking down; single replacement, swapping one; and double replacement, swapping partners. Recognizing these patterns helps predict what will happen when substances meet. Chemical change is everywhere, from baking bread to rusting metal. Understanding reactions lets us harness and control these changes. Chemistry is the science of transformation. Every reaction is a new beginning for atoms. Let's dive back into the atom and explore electrons through the lens of quantum mechanics. Electrons are not just tiny particles whizzing around a nucleus, they behave in ways that defy our everyday experience. In the quantum world, things get truly strange. We can't know exactly where an electron is, only the probability of finding it in a certain region called an orbital. Instead of following neat paths, electrons exist in fuzzy clouds where their exact position is uncertain until we try to measure it. Orbitals come in different shapes: S spherical, P dumbbell, and even more complex D and F orbitals. These shapes aren't just abstract math, they determine how atoms interact and bond with each other. Each orbital holds up to 2 electrons, and they fill up in order of increasing energy, the Aufbau principle. Think of it like a theatre. Electrons fill the lowest seats first before moving to higher rows. Electron configurations describe where electrons live in an atom, explaining the structure of the periodic table. These configurations are like addresses for electrons, telling us which orbitals are occupied. Elements in the same group have similar valence electron configurations, which is why they behave alike. This is why sodium and potassium, for example, react in similar ways. They have the same number of electrons in their outermost shell. The S block, P block, D block, and F block all reflect how electrons fill orbitals. These blocks help us predict chemical properties and trends across the table. This quantum view explains why bonds form and why molecules have their shapes. The way electrons are arranged determines if atoms will share, give, or take electrons to create new substances. It's the foundation of modern chemistry. Without understanding electrons, we couldn't explain reactions, materials, or even life itself. The weirdness of electrons is what makes chemistry possible. Their unpredictable behavior leads to the endless variety of substances and reactions we see. Every property, every reaction starts with electrons in motion. From the color of a flame to the rusting of iron, it all comes down to electrons shifting and rearranging. The universe is built one electron at a time. From the tiniest atom to the largest star, electrons are the building blocks that connect everything. Keep asking questions. The quantum world is full of surprises. The more we explore, the more we realize just how much there is left to discover about these mysterious particles.